We continue our scientific program, and the next talk is a colloquium by Nicolas Gisin. So the title is Indeterminism in Physics and Intuitionistic Mathematics. I hope I pronounced it well.
Well, the last word was perfectly well pronounced. Okay, thank you, Anton. Yeah, now I have to speak in all the micro. Okay, so welcome everybody, and let me start by raising the following question. I mean, who knows less mathematics than me here? Probably no one. One guy possibly, I'm not sure. Actually, so it's a bit strange why I am going to talk about mathematics or intuitionistic mathematics to you guys who probably know more than me about mathematics in general. Moreover, probably there are also several among you who know more about intuitionistic mathematics or constructive mathematics than I do. So what is my motivation here? You know, I'm a physicist, and some years ago I started thinking about some aspects of classical mechanics. I'll tell you more about that, of course. And that led me to actually start rediscovering intuitionistic mathematics. And then once I understood that, I learned a bit of that, and that's what I like to tell you about. So, so yeah, why does a physicist talk about intuitionistic mathematics? So, of course, here it is needless to emphasize that to do physics while speaking mathematics, you need physical concepts and you need mathematical tools and concepts so that you can speak mathematics. But which mathematics? Most of us, because yeah, we've been trained at high school and university, we think there is one mathematics and that's the one. But actually there are several forms of mathematics. And certainly here we all speak more than one language. We all speak English, we all speak some Russian or French or German or whatever. And so we all know that depending the language we talk, we can express some ideas in a easier or even maybe in a different way. So the language has a big influence on what we can say and how we think at the end. And so now, why intuitionism? I'll come back to that with my physical motivation, but maybe for those who know a bit about intuitionism, the father of intuitionism, this guy, Brouwer, his name will come up several times, he was a very special character. He was a super idealist, almost a solipsist. So very far from, you know, a physicist is a realist or a naive realist or something like that. Certainly not an idealist and even less a solipsist. And indeed, in Brouwer's view, he so introduced into his mathematics the concept of an ideal mathematician, a creating subject, who continuously produces new information by solving mathematical conjectures. That doesn't sound very physical. So I'm going to present intuitionism in a very different way, without these ideal mathematicians, and I will motivate it by the physical concept of indeterminism. And so, okay, I don't know, but I would guess that Brouwer would not have liked my presentation. But okay, hope you like it. So the main claim of my talk today is that intuitionistic mathematics is the natural mathematical tool to describe indeterminism in physics. Like derivative is obviously the good tool to describe the physical concept of velocities. So let's start simple. Numbers. Numbers are there to compute. Probably easy to convince you that this makes some sense. But if numbers are there to compute, how is it that actually almost all so-called real numbers are not computable? You probably know that essentially with probability 1, a real number is not computable, but numbers are there to compute. Starting to try to infect you not with a virus, but with intuitionism. Let's start even simpler than that, with real numbers, with integers. And let me define the following integer. n1 equals 0 if and only if every integer between 4 and 10 to the power 4 is the sum of 2 prime, and n1 equals 1 otherwise. Okay, probably you don't know the value of n1, but you would certainly be able to find out that value. Can tell you n1 is equal to 0. Okay, nothing very interesting in that. Can define n1 in this complicated way. Now, if I go on and define n2 equals 0, if every integer between 4 and a huge number is but finite number is the sum of 2 primes. Here, I guess no one is going to open his computer and try to compute it because it's going to take for ages and it will be, okay, no longer here to see the answer anyway. Still, it's only a finite number of steps, a huge but finite number of steps to compute n1. So n1 must have a value. Possibly it is 0, possibly it is 1. Okay?
Well, it's even, otherwise it's 1. Because, for example, number what?
Maybe you want to say...
Number 11 cannot be written as sum of 2 primes.
Okay, so every even integer, there is an even missing here. Yeah, correct, thank you, correct. So let's continue now with another one. So every even integer between, n3 equals 0, if every even integer larger than 3 without an upper bound is the sum of 2 prime. This is actually known as the Goldbach conjecture. Now here, even if you have a computer, super powerful computer, you're not going to find the answer in any finite time, or at least you cannot be sure. Possibly at some point someone, maybe one of you, will prove this Goldbach conjecture or will disprove it, but today we don't know. And now, what is the value of n3, or more precisely, n3 we don't know its value, for sure we don't know it, but does it have a value? There is no known method to find it. Now, if you're a good student, and I'm sure you have already all been good students or still are good students, you know that in order not to fail an exam, you claim that n3 has a determined value. Now, because if not, the statement n3 equals 0 would be neither true nor false. So the law of the excluded middle would not apply, so you claim, oh, it has to have a value. I don't know it, but it has a value. However, be careful, if the exam is in intuitionistic mathematics, then the student should answer that the value of n3 is indeterminate, and that the law of the excluded middle is not valid. So that's shocking. It's shocking to classical mathematicians to say something like that. But in some sense, you know, n3 presently has no value. At least there's no way in a finite number of steps to compute it. So let's go a bit more into this intuitionistic way of thinking. I have one more thing here. The value of n3 may evolve over time. That's also something shocking. If I tell you that a number can evolve in time. A number is not just a given in intuitionism. It is something that can change in the course of time. So time plays a role in mathematics, not only in physics. In physics, we know that time is important. Here in this language, mathematical language, time also plays an important role. And the value of n3, for instance, may change from indeterminate, as it is today, to determinate. Okay, so let's go a bit more into this intuitionistic standpoint. One philosopher of logic, Karl Posse, wrote, so we humans have finite memories, finite attention spans, and finite lives. So we can fully grasp only finitely many finite-sized pieces of a compound thing. There is no infinite helicopter that allows us to survey the whole terrain and to tell how things will look at the end of time. That's the standpoint of intuitionism. And another, not really intuitionist mathematicians, but a constructivist, Bishop, wrote, the classicist wishes to describe God's mathematics. the constructivist, to describe the mathematics of finite beings, man's mathematics for short. Constructive mathematics does not postulate the pre-existing universe with objects lying around waiting to be collected and grouped into sets like shells on the beach. And Brouwer wrote himself, so nature simply has not yet fully determined all objects. A bit like the uncertainty or indeterminacy principle of quantum mechanics. So again, if I don't tell you this particle is not there, and it is indeterminate whether it is there or not, that's okay, because we know that the particle could be in a superposition of here and there, so it means it is not really here, but it's also not really not here. But for mathematical objects, that's really very different and very new, and that's the crisp of intuitionism. So that's the essence of intuitionism. But I see that some of you, I mean, okay, now most people are not yet with the open computer, so you're still listening, very good. But I see that you get worried. I mean, how could there be things, including mathematical objects, that are not fully determined? Maybe to calm you a bit, let me emphasize that with this intuitionistic mathematical language, you can do everything that has been done in physics. Because everything that has been done in physics can actually be simulated, at least in principle. I'm not talking about practicalities, but in principle, you can simulate it on a computer, a classical computer. So since you can simulate it on a computer, and computers are finite objects, finite memories, and all that, obviously you can do all physics with that language. And let's take maybe an example, a quite timely example. Climate modeling, simulation of the climate in 50 years, in a century. How do people do it? I mean, the real practical physicists, like Tim Palmer in the UK, they use actually truncated numbers because they have so large numbers, and anyway, we cannot measure all these numbers. And then when they simulate the passage of time, they add what they call stochastic reminders. You know, because this is a chaotic system, at some point the late or the far down the series digits will become relevant. We didn't measure them, we don't have them in the computer, they need them, we just put it stochastically in. That's how actually climate modeling and simulation is done. Maybe a different way also to look at all this is with this tension between relativity, with the block universe picture where everything is fixed since and forever, and on the other side, quantum randomness, where you really have new information that gets created as time passes. Just be a bit careful here. Yeah. Kim, now let me open a little bracket, because actually I'm not a mathematician, as I already said, I'm almost the opposite, I'm a quantum engineer. And one thing which I like also to do, besides thinking about intuitionism, is this kind of stuff. And so what we did with our startup IDQ, ID Quantique in Geneva, is to take this idea, very simple principle, do a lot of engineering until you can put it into a chip, millimeter size, microwatt power, so very low power. And once you have this chip, you can contact, for instance, Samsung, and integrate that chip into their smartphone, and then must have an application that uses it. And for instance, now you have some mobile banking application that is using this quantum randomness. Today, this is only available in Korea, but maybe in a year's time, people in this audience will have a quantum random number generator in their pocket. Okay, this is not science, so let me close that bracket and come back to physics, to science and physics here. So this is now my motivation, actually, how I came to intuitionism. So we know, okay, deterministic chaos. Okay, on my computer, this is moving and you see Brownian motion, but you can, with a little bit of imagination, understand that. Okay, and this is termed deterministic chaos. No, classical mechanics is supposed to be deterministic. We all know that. But is that really so? Is classical chaotic dynamical systems really always deterministic? Or is it the consequence of using the language of classical mathematics? So of assuming a God's eye view from the end of time. And so this other philosopher wrote tense and passage of time are not, never were, and probably cannot be part of physics and its language. Because indeed, if we use classical mathematics and real numbers, nothing is going to evolve. Let's take a very simple example of a chaotic system, which is essentially the Baker map that you probably all know. So you have the state space is just a number between 0 and 1. You stretch it, and then you fold it back. So this is the function or the map here. And this map, when you express it in, with bits in binary format, so because it's a number between 0 and 1, it's 0 dot, and then you have a series, an endless series of bits. And the map just shifts all these bits by one position to the left. The first one drops out, and so on. The second one becomes the first. So pretty obviously, whether x lies in the left half or the right half after n steps depends on the nth bit of the initial condition. Now you may say this is the probability of raining or something like that, so weather forecast or something like that. And now the question, is the millionth bit physically real? Of course, the question is not whether you can measure it. For sure, you cannot measure it. But is it physically real? Is it really there, out there in nature? Does it correspond to something physical? So let's look at these typical real numbers. I guess many of you know all that, but still let's look at it. So all the real numbers that we actually meet in everyday life, okay, maybe there are some too abstract. Anna, maybe you meet real numbers that I have never met, but you know, the numbers that I meet, they have names, they have an algorithm, they are computable, and they are exceptional. They are not typical. Because the bits of typical real numbers have no structure. The bits are random, or quantum measurement outcomes. So maybe a good way of thinking of a real number, a typical real number, is just like that. The typical real number, the digits or the bits that come out, is just what comes out of a random number generator. And actually the connection is, I think, even closer to than that. Also, Gregory Chatin, for instance, emphasized. Yeah, that's the obvious thing. Yeah, also something that Emile Borel said about the real numbers. You know, because in a real number, you have infinitely many independent bits, or with finite correlation, but so you can code infinite information. And if you can code infinite information, among others, you can code the answers to all questions one can formulate in any human language. And so the only good way of thinking of a typical real number is exactly that. The bits of a typical real number are random, like what comes out of a random number generator. So when we say let x be a real number, for instance, initial condition of some chaotic system, what we're actually saying in between the line, let x denote an infinite amount of information. So saying let x be a real number is not a small thing. It's an enormous thing. You're making an enormous assumption by saying let x be a real number. You're already, you know, taking this God's eye view. You are that powerful that you can give infinite information in 0 time. Now, from a physicist's point of view, if you have a finite volume of space, it makes sense to assume that you can only have a finite information in it. You have even ways of deriving that and so on. But just let's say that's an assumption here. And then it means that if you have some kind of billiard ball in your finite volume, the center of mass of that finite volume cannot be represented faithfully by a real number, or at least not by a typical real number, because that would put infinite information into your finite volume of space.
Or do you say that the space is discrete, the space we live in?
The space is not discrete, but the way we describe it is evolving in time, and at every finite time, you have only finite information.
It's like inherently discrete, or we perceive it as discrete.
The best description we can give of it, especially if we want to have an open future description, is with finite information.
Yeah, but here, do you refer to general relativity? You said one can...
No, yeah, we can indeed, that's the Bekenstein bound, and we can indeed derive it with Bekenstein bound, but you know, that calls in then general relativity, black holes, and all that. And I think we can easily buy as an assumption that finite space contains finite information, and let's just take it as an assumption rather than deriving it with this heavy general relativity, field theory, black holes, and all that. But it doesn't matter. It's just a motivation to say, I mean, you know, I'm trying to get into your brain that real numbers are not something obvious, although, of course, we have been selected for our ability to swallow all that. Continue? Voilà. So it's certainly not because Descartes named real the so-called real numbers that they are really real. So actually, mathematical real numbers are not physically real. Mathematical real numbers are physically random. Consequently, this cannot be the basis of scientific determinism. So that's the way I came myself to intuitionism before knowing about intuitionism, and I had this kind of intuitive picture. Now, if you have a number, the first digits, they are determined. Then they get blurred, and after a while, they are undetermined. Okay, so, okay. So whether Newtonian classical mechanics is deterministic or not is not a scientific question. It depends on the physical significance when associated with mathematical real numbers. So somehow it depends on the mathematical language you are going to speak. And that's the last, I think, philosopher's quote. Then I come really to intuitionism. So Elisabeth Anscombe, who was a student of Wittgenstein, wrote, "The high success of Newton's astronomy was in one way an intellectual disaster. It produced an illusion, for this gave the impression that we had here an ideal of scientific explanation, whereas the truth was it was mere obliqueness on the part of the solar system by having had such a peaceful history in recorded time to provide such a model." Okay, so now I'm introducing some indeterminism into classical mechanics, like we have indeterminism in quantum mechanics. So first, I like this idea of bringing quantum closer to classical, classical closer to quantum, while people usually do always the opposite. But anyway, once you have indeterminism, a very natural reaction is to say, oh, this is due to some ignorance. We should add something. There's something missing, and that's the reason why we believe this is indeterminated. So we add some supplementary variables. So in some sense, we say that instead of God playing dice when potentialities become actual, God plays all the dice at the initial time and coded all results in the initial condition. So we face a choice. Either the fact that at present certain things happen and others do not is interpreted as revealing retroactively information about long past initial conditions, or else we understand the present as the result of indeterminate reality and the future is open. So if you think like that, you conclude that actually the real numbers we are used to are the hidden variable of classical mechanics. Like you have also hidden variables for quantum mechanics. They have to be non-local because of Bell inequality, but you have non-local variables, hidden variables, like Bohm's model. And it is a fact that almost all physicists accept real numbers without even noticing that these are supplementary variables, while simultaneously rejecting Bohmian positions as unnecessary. So that's probably more a historical fact. Okay, let's come now to the big debates. So there are these big debates, Einstein-Bohr, you all know about that. Einstein, who met also Bergson, who was the leading philosopher of that time, and they talked about time, and Einstein somehow convinced not Bergson, but the community that time is an illusion. But there was another more relevant for us debate at that time, almost at the same time, between Hilbert, very well known, don't need to be introduced, who was defending classical mathematics, the one that we all know, and in which every real number is an individual completed entity. All digits are given at once, and the continuum is just a collection of individual points. On the other side, you have someone who is much less well known, this strange character, Brouwer, this almost solipsist guy, who is the father of intuitionistic mathematics, and for whom real numbers are processes that develop in time. Digits are not all given at once, except for computed number, and so the continuum is a viscous collection, I'll explain what I mean by that, of processes. And so for Brouwer, time is essential. For Hilbert, there is no time. We are looking at everything from the end of time. So intuitionistic mathematics. So Brouwer introduced the terminology of a choice sequence, alpha n, where the choices were made by this ideal mathematician. But let's think now more in terms of physics. Let's just assume that nature has the power to produce true randomness, so to produce new information. And if indeed you are interested, like me, in describing indeterminism with an open future, with time really passing, it means that something has to happen as time passes. And what else besides new information? So I think it makes a lot of sense to start with that, and I call that a natural random number generator. So it's nature who produced that. And once we have these these random numbers, Rn, at every time step n, we can compute the elements of Brouwer's choice sequences. So we define that as follows. We assume there is a function which determines the nth step element of the choice function that depends on the previous value on the time instant and all the finite available information. So everything that this natural random number generator has produced up to this point. And this function should produce a computable number and be a computable function. Okay, and then Brouwer was always saying, so this series has to converge. So I'm writing here, it converges with priority one. You will see examples, and in one of the examples, I need probabilities. And here, I have to admit that I'm a bit vague and probably not fully satisfying because probability, again, introduces real numbers.
Sorry, who of them is random? So R or alpha?
R like random. So this is a bit. For each n, this is a bit, so 0 or 1. And with probability 1/2, 1/2. Mm-hmm. Now you use these bits, so here n bits, as an argument of the function. Mm-hmm. Okay? So instead of these mathematicians producing new information, is my natural random number generator that produces new information. So let's look at some examples. The first example, which is now probably pretty obvious, you use this nth output of the random number generator as nth bit becomes the next bit. So at each time you have only finitely many bits, but the series of bits is going to grow. So you have really the intuition of a real number, but at finite time, finite information. On the other extreme, maybe computable numbers. They still exist, of course. And for instance, if the function depends only on the k first random numbers, then this is exactly what we have in all our computers to generate pseudo-random number generator, a pseudo-random number series. So you can have all these pseudo series, but you could also have a number like pi. Pi is the typical computable number. All digits can be computed. And I think there is something more. Let's suppose you want to access the second million digit of pi. Well, you can start computing the first, the second, and so on. And after some time, you'll be at 1 million. And after more time, you'll be at 2 million. If you want to know what is the weather in Sun and Meuse in 2 years' time, possibly this is undetermined. But what you could do is just to wait 2 years. In 2 years' time, it will be determined. And to get there, in 2 years' time, you first have to wait 1 year, and then you wait a second year. It looks like pi. But there's a very big difference. With pi, you have formulas like that one, which allows you to compute the nth, okay, hexadecimal or decimal of pi without computing the previous digits. And I think this is a superb example of the difference between something which is a process that has to develop in time and where you cannot jump 2 times ahead, you have to go one by one. And for a computable number, you can jump wherever you want and directly compute that digit. So I think this is a good illustration that the digit of pi don't come one after the other. They are already there. They are all there. So here comes another example of intuitionistic numbers. Finite information quantities. And I think this is a good example, pretty close to physics. Again, you have a function, but this function now doesn't just look at the last random number, but looks at the last k ones and takes the majority of them. Let's suppose k is an odd number, so you have a majority. And so the majority will be the next bit in your series of bits. Okay, so now you introduce a bit of correlation. It's finite correlation, but you have some correlation, not totally random. And we expect, I mean, relevant real numbers, relevant for physics, they're not totally random. They must have some correlation. The weather is not completely changing from a minute to the next one. And so when you have that, you have some bits that are fully determined, 0, 1. Then you have some, so this is at time n. So this is the nth element of the choice sequence. So up to n, they are fully determined because there is always a majority. Then there might be already a tendency or a propensity because you have maybe already a large majority, so to overrule that majority is unlikely. So you have some propensities, and then you will have the totally undetermined bits. And you have here an example. So here you have a clear majority of 1. So the next bit is a 1. Then if I look only at the last 4 1 and take the 5th one here, which I don't know yet, but whatever this 5th one will be, the majority will be a 1. So the next one is a 1, and so on. Then here I have a majority, but I have 2 more to take. So the 2 additional ones could both be 0, and that would overtake the majority. So the probability or propensity of a 1 is only 3/4. Can you dismiss that? Il faut faire quoi là? Oui, mais pour ça, là. So I don't have a pointer, that makes it more difficult. Here it is. Okay, so on. And then you can continue, and you have, of course, now. Merci. Okay, so now let's look at another example. This is still a very standard example in intuitionistic mathematics. Okay, it's my terminology to call them mortal number. Here the idea is that, okay, here now it's with, okay, I put bits instead of, digits instead of bits, but doesn't matter. So -1 to the power of this random number, and it gets further down the series. So this is clearly a theory or a sequence, a choice sequence, that is fluctuating between just above and just below 1/2. It's just fluctuating there. And let's suppose that this function, this computer function, is such that this continues until by chance the last n/2 random bits all happen to have the same value. And of course, n is even and larger than 4. So it can continue forever, this fluctuation around 1/2, or maybe at some point, by chance, it stops just above 1/2, or it stops just below 1/2. Somehow the process dies, or the number dies. And once it is dead, it stops there. And not because of this probability goes down, it decreases exponentially, because the longer it comes, the smaller the chances of dying. There is an a priori probability that one, of course, can compute that the sequence goes on forever. So you already have 3 possibilities for these kind of numbers. It could go on forever, and you will never know whether it is smaller or larger than 1/2. Or it stops below 1/2, or it stops above 1/2. It's not a binary choice, 3 possibilities. So the proposition alpha is smaller than 1/2, so the limiting now, but alpha, it is at the same time the series and the limiting value. So this probability, this proposition alpha smaller than 1/2 is neither true nor false, but indeterminate. One more example, that's the last example. That's the example where I need probabilities. And this is not a standard example that you find in textbooks, but you understand why I want to present that. I call that autonomous numbers. So far, in all these examples, the function did always explicitly depend on n, on the time step. So it's not autonomous. And because of this explicit dependence, you can guarantee convergence. But let's now have this function here, which does not depend on n. And you see, so there is some stochastic terms here, plus or minus 1, some convergent parameter, mu, which is just fixed rational, and then this nonlinear function here. So clearly 1 and 0, these cancel, so are fixed points. Once it reaches 1 or 0, it stays there forever. But you can also prove that alpha of n is going to converge to 1 with probability alpha 0, or converge to 0 with probability 1 minus alpha 0. So you have this convergence which is built in, but it's probabilistically converging. You cannot guarantee that it's converging. That's why I need probabilities here. So now, okay, and this is also known as the gambler's ring problem or something like that. So you model that in many situations. And, oops. One situation where you use that, I used it many years ago, and people in physics, the people who want to add some terms, some stochastic terms to the Schrödinger equation in order to describe the collapse and have indeed also an indeterministic evolution equation instead of the deterministic Schrödinger equation, they use those stochastic Schrödinger equations, Girardi-Rimini-Weber model or quantum state diffusion. It's the same type of equations. And this equation is such that if you start with a superposition of photon number, quantum number, let's say the odd numbers 1, 3, 5, 7, and 9, and here you have the expectation value of this photon number, in function of time, each solution converges to an eigenstate. So you really get this collapse described by these equations. And the probability of collapsing to any of these numbers, let's say 5 here in this example, corresponds exactly to Born's rule. So it corresponds exactly to the quantum probabilities according to standard quantum mechanics. And if you would now look more into these models, which I'm not going to do here, this is really using exactly this kind of evolution, except that you have more than 2 terms because you have as many fixed points as eigenstates. So this again brings intuitionism brings classical mechanics closer to quantum. Okay, so that was really just to have some choice sequences. But now, of course, in intuitionistic mathematics or in any mathematics, you must also have some logic. And indeed, so now time is essential. We have seen that. And so the statement Rn equals 0 is indeterminate before the nth time step. But also, as we already saw, this mortal number alpha smaller than, and the proposition alpha smaller than 1/2 is indeterminate as long as the mortal number didn't die. And this is really to be associated with the physical proposition, it will rain in exactly 1 year time in San and Meuse anywhere, which is at present indeterminate. But you can wait and you will see. But now here, again, comes this very central and important aspect of intuitionism, which really differentiates it from the standard mathematics, is that this law of the excluded middle does not hold. And because it does not hold, non-constructive existence proofs are not valid. So we lose a lot of our proofs techniques. We can no longer, it's not sufficient to prove that something, you know, that the non-existence of something is a contradiction to prove that it exists. And that is very surprising. And that's probably coming as a surprise, if not a shock. But again, if you think in terms of an indeterministic world, a world in which the future is open, it makes a lot of sense. And again, Brouwer says that the law of the excluded middle fails because the world is not determinate, including, according to Brouwer, the mathematical world. So truths about it are indeterminate. Let's look now at the intuitionistic continuum. Let's see the, you know, the line between 0 and 1. So elements of this continuum, which one may call the intuitionistic real numbers, are really evolving sequences of computable numbers. Brouwer would have said rational. He didn't use computable, but rational. But I think computable make more sense for physics. So the elements there are not just points. They are processes that develop in time. And for some sequences, it is never determined at any finite time whether they are larger or smaller than any computable number, like 1/2. And so, sometimes going too fast. And so one cannot cut the continuum into larger and smaller than 1/2. You know, 1/2, we think that's a real, okay, it's a fraction, a very simple thing. It's in the middle of our interval. Classically, you can just take it out. Or what you could do is have a function which is a step function, 0 up to 1/2, and then equal to 1. We have all used such kind of functions. But now if the function is of elements of the continuum, of the intuitionistic continuum, you have some of these choice sequences. You don't know whether they fall on the left, so they should be mapped to 0, or whether they fall on the right, so they should be mapped to 1. So the consequence of that is that, that's okay, one of called Brouwer's theorem, that all total functions, so all functions defined everywhere, are continuous, no step function. So this is an example of a theorem which is correct in intuitionistic mathematics, but of course not correct in classical mathematics. And in this sense, this intuitionistic continuum is viscous, because it's like honey. You cannot take out a grain of honey. No, there are no grains in honey, so it's sticky or it's viscous. And that's the meaning of the saying that the continuum is viscous. Now something else which comes out of that, which is also maybe shocking, have a function that starts at the negative value, let's say, and then becomes positive. And it's a continuous function. So you all know about the intermediate value theorem, so it has to cross 0 somewhere, isn't it? Well, not according, sorry, I should say it first. Not according to intuitionism, because the existence of this point where it crosses, this real number where it crosses 0, my continuous function that starts negative becomes positive, I cannot construct the point where it crosses 0. And because I cannot construct it in a finite time, I cannot prove the existence of that. So the the intermediate value theorem, which is of course valid now in classical mathematics, is not valid in intuitionistic mathematics. However, and that's very typical, which essentially says what you want. Namely that if you have a continuous function that starts negative, becomes positive, then for every epsilon, one can construct now, in a finite time, intuitionistic real numbers, an element of the intuitionistic continuum, for which the absolute value of f of x is smaller than epsilon. So that's actually what we really use when we want to apply the intermediate value theorem. But this is an example where, again, the theorem itself, the classical theorem, is intuitionistically not correct. And then there's another example, which is Gisin's theorem. So Gisin's theorem is a very important theorem in quantum mechanics. And the way Gisin's theorem is usually proven, and certainly the way Gisin himself proved it, is not valid intuitionistically. However, and that took some time, someone, this man, Richman, could prove Gisin's theorem, but using a different proof technique. So you have theorems that are valid in one mathematics and not in the other, and vice versa. And you have theorems that hold in both, but need different proof techniques. Intuitionistic arithmetics. So if you have two of these choice sequences, obviously you can add them, you take the sinus of them. So that's where I'm using computable number, not rational, so that computable numbers are mapped onto computable numbers by computable functions. And then you can also have an order relation, alpha larger than beta, and it runs the same way as you would expect, with the only difference is that, these integers k and n that you need to find in order to prove that alpha is larger than beta, they have to be constructible in a finite time in intuitionistic mathematics. And because of that, this order relation is only a partial order. And even something like alpha equal beta or alpha smaller than beta or alpha larger than beta cannot be proven in general in intuitionistic mathematics. Again, whether alpha is equal to 1/2, smaller than 1/2, or larger than 1/2, you cannot prove it in a finite time because you just don't know. It is indeterminate. However, you can introduce something which is not exactly the same as equality, but it looks like we say alpha beta apart if one can construct, the usual k and n such that the absolute value is larger than 2 minus k. And then you can indeed prove that if two elements of the intuitionistic continuum are not apart, then they are equal. That's intuitive. But on the other side, if two numbers, intuitionistic numbers, are not equal, that does not mean that they are apart. Again, with these numbers that oscillate or fluctuate around 1/2, they are not equal, they are undeterminate, and that doesn't mean that you can stick your finger in between, so they're not apart. Something else I wanted to say, which is not directly about intuitionistic mathematics, but I think it's the same spirit, so let me just have 1 or 2 slides on that, coming close to the end. Axiom of choice. Probably we all have used the axiom of choice, no? Super nice axiom. Whatever collection of non-empty sets, there is a function that allows me to pick one element per set. And it's pretty obvious, no? Because the sets are not empty by assumption, then of course I can take one out. That's the meaning of not being empty. But on the other side, this axiom is absurd because it implies the possibility to make a continuous infinity, let's suppose the index is continuously infinite, of choices in a finite time or in no time. And again, so in the spirit of intuitionistic mathematics, this is obviously impossible. You cannot make infinitely many choices in 0 time. Yeah. So this axiom certainly gives us a superb feeling, a godlike feeling. We are doing God's mathematics in general. So in a single stroke, we can make continuous infinity of choices. Wow. But when we apply that to the real world, it becomes absurd. One of the consequences, proven herein, of the axiom of choice is the existence of a function that predicts with probability 1 all future events, including the outcomes of a true random number generator. So this axiom of choice is that powerful that you can prove in a non-constructive way, obviously, the existence of a function that gives you the weather for the next, well, for eternity, with probability 1. It essentially never fails. And so physics intuition that we should describe the future as open, there cannot be a function that describes the future if the future is not yet determined. So somehow you can say, I would like to say, keep this axiom of choice for Platonistic mathematics, but reject it for mathematical physics. Okay, I'm sure that several of you will disagree, some maybe strongly, but never mind. So the mathematical language we use when we speak physics has huge influence on the worldview that physics presents to us. And just like to share a table which shows you how closely intuitionistic concepts and indeterministic physics are related. For instance, in deterministic physics, we would say that the past, present, and especially the future are not all given at once. But that's exactly the idea that the digits or bits of real numbers are not all given at once. Time passes. Numbers are processes. Time enters into mathematics. Indeterminism. Numbers contain, okay, with one S too much, only finite information. The present is thick. The continuum is viscous. The future is open. There is no law of the excluded middle. I think that's also going well hand in hand. Becoming, choice sequences, experiencing, intuitionism. So that's what I would like to be able to describe, and I think this language is well adapted. Okay, so I just wrote some summary. There's maybe one thing I can say on that, because maybe some of you would like to read something, and I have to say that it's very difficult to find a book on intuitionistic mathematics. There's actually one, this one by Carl Posse, but it's in press. So it should come out in a week time or in a month time now. It should come out soon. And this is, to me, the best book on intuitionism. Then you have articles and so on, but I find the rest is pretty obscure quite often and is never presented in this physicist language as I did today. Okay, thank you very much for your attention.